Okay. Yeah, thanks for the introduction. So this is also about probabilistic programs. This is about Caesar, our deductive verifier for probabilistic programs. This is based on joint work with Batz, Kaminski, Joost-Pieter, Katoen, and Christoph Matheja, which was published at OOPSLA last year. So as a first example, let's look at another probabilistic program. This is what we call the geometric loop. It produces a geometric distribution. So as you can see, it's just one while loop, two variables, and then we have this probabilistic choice over there. And here with probability 50%, we set run to false and so terminate the loop. And with 50% probability, we increment C. And you can kind of imagine this as you flip a coin and you stop when you hit heads, and you also count how many iterations you do. So we can look at various different properties of this program. And so one very simple one is, what is the probability that we terminate in a state that satisfies C equal to 1? Okay, you can maybe run this, look at this. This is 25%. Then a bit more complex or more interesting is, what is actually the expected value of this? So this is an infinite sum here, and the infinite sum evaluates to 1. So an expectation, or the expected value at the end of this program is 1. So you can see this as, on average, we do 1 incrementation of C. Then this program can diverge. So there's one execution going always to the right-hand side branch where we do not terminate, right? But the probability of termination of this program is 1. And so we call this program almost surely terminating. This is also a property that we might want to verify. Furthermore, this program is what we call positively almost surely terminating. So the expected runtime of this program, let's say this is the number of times we evaluate the loop guard, is 2. Okay, so because the expected runtime is finite, we call this positively almost surely terminating. The probability of termination is 1. So these are two separate properties that we want to verify and need to distinguish. So in general, what we wanted to look at was various different properties. So we wanted to look at lower and upper bounds of expected values of probabilistic programs. We want to look at stuff like expected runtimes, almost sure positive, almost sure termination, maybe amortized expected runtimes, and more. So there's other properties like probabilistic sensitivity, which describes how much does an output change depending on a change in the input, relevant for differential privacy, or conditional expected values, expected resources, and so on. And then on the right-hand side here, or I guess your left, there's proof techniques that we want to use. So this is just a small number of them. Proof we'll call Park induction is kind of what you might know in the classical setting as just your standard Hall logic rule for loops. Then we have K-induction, martingale-based reasoning, and more. And our goal, of course, was how do we automate reasoning and verification about probabilistic programs, so especially verifying properties that we've seen before. And how do we make this extensible? So how can we add more properties afterwards, add more proof rules to reason about these programs? And our idea was, hey, let's build the probabilistic version of Boogie or Viper. So we built an intermediate language to encode verification problems for probabilistic programs. And so this is what Caesar is based on. So Caesar uses our quantitative intermediate verification language that we call IVL. And we encode the program, the specification, and the proof rule into IVL. And then we have semantics of this language that we call verification condition generator that generates an expression in a real value logic that we call halo. And so then we encode, as I said, all of this stuff into IVL. And in the end, we have our implementation Caesar that takes such encodings and then uses an SMT solver to try to prove correctness. And yeah, this is all integrated into our tool. So let's see how these specifications look like more closely. So in the classical setting, you might imagine you have a Hall triple with pre and post condition. Let's imagine we have total correctness. And we have a pre and post that are Boolean. So each state, that's the sigma, is mapped to true or false. And what the specification might mean is, for example, P describes a subset of the states that terminate in Q. Okay, so we can write this using weakest preconditions, really saying, okay, P is a subset of the weakest preconditions of Q, and you can see also that weakest precondition reasoning really is this backwards kind of reasoning. And what's cool about these classical IVLs, and which you probably know from Dafny', right, is that you can use assumptions and assertions. You can assume that P holds before the program, then you run your program, and then you assert that Q holds afterwards. And this is something that we want for expected value reasoning as well. So what does this look like in expected value reasoning? Well, we have a pre-expectation and a post-expectation, F and G respectively, and now each state each state sigma is mapped to a non-negative real value or infinity. Okay, so now we reason about expected values and assign each state such a number. And what this is supposed to mean is F is a lower bound to the expected value of G on termination of G, of the program. And so we have a generalization of weakest preconditions to the probabilistic setting, which is known as weakest pre-expectations. And what's cool about our intermediate language is that we also have now these variants of assume and assert statements. So we can assume F and assert G, and now F and G might evaluate to numbers. So we can literally write assume 2, assume 5, which is something different than saying assume X is 5. Okay, so we'll see how that works in the following. So the idea is that we look at semantics, or that we look at semantics by defining a logic to reason about expectations, so expected values. Let's just define the semantics of an assert statement as a minimum. So if we assert an expectation F and we have a post expectation G, then we just take the minimum of these two values in each state. Now, a big question for us was, how do we define the semantics of an assumption? What should an assume statement mean then? It should be some kind of implication, right? But now this implication is between expectations. So F and G can evaluate to numbers, and the result should also be something that evaluates to numbers. And we looked at a couple of properties that we wanted to have. And one is from hating algebras, which says basically that if you have an implication G implies H, and we have a lower bound F on it, then this should be the same as basically pulling down the left-hand side, saying the minimum between F and G implies H. And you can kind of read this in the Boolean setting, saying, okay, if you introduce an implication G implies H, and you have a pre-F before it, then that's the same as introducing G as a pre, so making more assumptions. The other property that we wanted to have was really being able to encode kind of exact comparisons. So this deduction theorem here says F is a lower bound to G if and only if our implication that we're defining is equivalent to infinity. So imagine infinity something like true, and this means really we can encode comparisons with this, which is very important doing comparisons when you're doing probabilistic reasoning for our probabilistic proof rules. So the definition that we arrived at is something that I'll show you with a picture. This here is 42 implies G, right? You can see 42, this is just a number, and the implication, this Gödel implication here, named after Kurt Gödel, is supposed to mean something like assume any value G at least 42 to be true, okay? So from the definition, this means that if you plug in anything up here, then you get infinity, kind of like true. And if you plug in anything less than 42, then you get the identity function. Okay, so this actually generalizes the classical implication to the probabilistic setting, to the quantitative setting, and works pretty well for us. So, okay, so let's run an example. This is the loop body of the example that I showed you in the beginning. We now clearly assume something quantitative, right? We assert C, and C evaluates to a number, and we assume C plus 0.5. And to check whether this program now verifies in our quantitative setting, we check whether the semantics going bottom up evaluates to infinity. So we start at infinity and check whether that's infinity. Same as starting with true and trying to see if true is a result. So we assert C, and what the result of the semantics here is that we take the minimum between C and infinity, which is just C. Then we compute the expected value of this probabilistic choice, which is, in this case is fortunately very easy because there's no loops, nothing complicated happening. So this expected value is with 50% probability you get C, with 50% probability you get C plus 1. Yeah, okay, you can simplify this and then you get C plus 0.5. And as I said, the assumption now generates this implication. How is this supposed to be read? C plus 0.5 is at least C plus 0.5, so we get infinity. Okay, a very easy example. So the final result is infinity. We started with infinity, which means by our definition, the program verifies. And by the correctness of this encoding here, this really means that the expected value of C after running this program is at least C plus 0.5. So that's kind of how stuff works, how encodings work in a very basic setting here. Now, this is IVL, this is the basics. So we've seen the assertion, we've seen the assumption as minimum and the Gödel implication, and we have a non-deterministic choice that in the quantitative setting here corresponds to an infimum. And if you look at the classical semantics, right, in the classical setting, it's a Boolean AND, okay, corresponds to minimum. Classical Boolean implication corresponds to this generalized Gödel implication, and the for all corresponds to the infimum. So IVL really generalizes classical intermediate verification languages, and we actually have a theorem for this. And then there's a second thing that we needed, which is very natural in the probabilistic setting to think about. Why not think about, we want to think about upper bounds of expected values, not only say the expected value is at least something, but also say it is at most something. Imagine the probability of an error being at most, 50%. And so what we added was these dual statements for reasoning about upper bounds of expected values. Co-assert, co-assume, co-havoc. Co because they're really just the duals. So we now have a maximum between expectations for co-assert. For the co-assume, we have what we call a co-implication. It's just basically flipping the directions, flipping the arrows. You can see the full definitions in the relevant paper. And the co-havoc is, not surprisingly, the supremum. So this is allowing us to do upper bound reasoning in this language as well. Maybe you also see a relation to this. What you could also do, for example, is try to do incorrectness reasoning with this, because this is also upper bounds reasoning. So to show you that this idea works, we implemented this, of course, in our tool Caesar, and we have more than 40 examples of probabilistic programs that we've verified. So we have 12 different proof rules for loops, which shows you there's not just one proof rule, not just induction. There's much more. So we have lower and upper bounds on probabilities, kind of like partial correctness. Then we have lower and upper bounds on expected values with proof rules like k-induction, omega invariance, and so on. And we also want to reason about conditional expected values, expected runtimes, as I said. And we have also two separate proof rules to show almost sure termination, or specific proof rules to show almost sure termination and positive almost sure termination, showing that you can really encode a lot of stuff into this intermediate verification language. These examples also include procedures. We have recursion in there, user-defined data structures. A lot of stuff that you would expect. So let's see how one proof rule works, namely the simplest one, the induction one, the standard loop rule. So just like in Dafny, to reason about while loops, we can use invariants. And in the classical IVL, how you would encode verification about a loop is something like this. You have a Boolean invariant, a predicate, and if you have a loop while b do as, then before the loop you assert that the invariant holds. Then you enter the loop, that's the havoc statement, and you forget kind of everything about the modified loop variables. Only you assume that the invariant holds in the beginning. Then if you enter the loop, you run the loop body once, and then you need to assert that the invariant holds at the end. And the assume false kind of means you don't run afterwards. But if the loop body does not hold, you just continue with your program. And in IVL, this looks almost exactly the same. Again, I is here an expectation, so it can evaluate to numbers, but we still have this assert, havoc, assume thing going on, with the only difference being really in the encoding that we have this additional validate statement here, which is unfortunately necessary in the probabilistic setting, but we have more explanations why this is important. But yeah, so you can see definitely that we have a really nice generalization that of classical IVLs that also generalizes the encodings of classical proof rules. And of course, this is sound for probabilistic programs. So we have a website, caesarverify.org, for our tool, Caesar. It's written in Rust, it's open source. We also have a bit of language documentation and an extended version of our OOPSLA 2023 paper, where we describe all the theoretical details of HVL and the rest. So in the language, you really can see the semantics of HVL and halo this logic to reason about quantities, and some more detail on the case studies that we've encoded and verified automatically. Yeah, thank you.
Thank you very much for the excellent talk. I have a question of a more theoretical nature. I was wondering how much of the theory you've built actually realized that you're working with reals with extended infinity, and how much of it, for example, holds in quantalic setting or in some sort of residuated semilattice setting. And maybe if you take a Boolean quantile, does it become like ordinary Boogie-like language?
Yeah, so we kind of, the reason why HVL is called HVL is because of hating algebra. So I think quantiles are kind of other structure a bit. But you can definitely instantiate just this framework with just Booleans, and then you get just the Boolean stuff that you would expect. So then it's just, yeah, I would say Boogie's Boolean semantics. You can plug also in other stuff, like just 0-1 bounded stuff, but this is not what we focused on now in this paper.
I guess it will be some sort of intuitionistic Boogie then?
Yeah, you can think so, yeah.
All right, thank you very much.
But this, like, generalization is future work, yeah.
Thanks, that's very neat. Have you thought at all how you might integrate this with, say, a non-quantitative valued logic for verifying the rest of your program, perhaps that's not randomized?
So, I mean, for Boolean logic, we can easily integrate it. I mean, it's just, you map everything, you map false to 0, you map true to infinity, and then you're done. So, kind of just Boolean reasoning works just out of the box easily. Yeah, and I think that's basically the answer. So, really just, like in theory, you can just take your normal Boogie program, and if the language features are supported, then you literally just transpile it and have, and add maybe some conversion to 0 and infinity, but that's about it.
Okay, thank you. Okay, let's thank Philipp and have the next speaker get ready.